Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. I kind of missed the flat Earth, so I went into Gem Panda's chat today and I had a chat with a couple of people that were talking about why rockets can't work in space. So I thought I would go ahead and have a look at the videos that they put up and maybe give them a little bit of an answer. So let's cue up the music and get going. So why do rockets work in space? Well, it's actually rather simple. Say this is a rocket. Here's the nose cone, and the rocket engine is down at this end. When this rocket engine lights off, it throws large amounts of mass out of the back end of this rocket at very high velocities. And as you can see by Newton's third law of motion, wherever there's an action, there's an equal and opposite reaction. So as the rocket exhaust is thrown out the back, the rocket goes forward. There you go. That's why rockets work in space. And that's really the end of it right there. Nothing more needs to be said. However, the reason debunkers like me exist is there are people out there that really have problems understanding this concept. So let's go ahead and have a look at some of the evidence this flat earther put out. I think you'll get a kick out of it. We'll identify where their misconceptions are and give the correct answer. So let's go. Now, when this gentleman made this assertion that rockets couldn't work in space, he based it on an experiment on a YouTube channel that he found. And here's the YouTube channel. Let's have a look at it together. Now, he starts off with this piece of wood on a table. Now he has a car with a balloon attached to a straw. And what he's using that for is once he lets the straw go, air will rush out of the balloon and out the nozzle of the straw at the other end. Let's see what happens to the car when that happens. Okay, goes across the table. Now again, it would be really nice to see whether or not this table was level. He doesn't show anything. He doesn't show any measurements with this, which is pretty typical of flat Earth experiments. Now he's going to weigh the car and show how much the thing weighs. It's a very light car. It looks like about 107 grams. So what he's doing is he's going to go ahead and repeat the experiment. And again, look at the speed the car goes by. No problem. Now he's going to put a couple of coins in the car to add a little bit extra weight. This will increase the friction on the tires, and we would predict that perhaps the car would move a little slower. Let's see what happens. Well, it does. Okay, now let's get to the heart of his experiment. He's going to put the car up, and he's going to take a vacuum hose and put it by the end of the straw. Now, I guess he's trying to pull some sort of a vacuum or suck up all of the exhausts with that vacuum hose. I have a lot of trouble believing that he can create a localized vacuum behind a car using a vacuum cleaner hose. I also doubt that he can actually pull all of the air that's coming out of that straw into that vacuum hose. Now, when I first saw this today, I happened to notice this, and I want you all to notice it as well. Now, I'm going to pop my head out of here for just a second because I want you to see this very clearly. I want you to look at the balloon on top of the car. Now, notice it's hooked up to the end of the straw, which is horizontal, but the balloon itself is going vertically. Watch what happens as it deflates. See what direction it tilts. See how it goes forward? He's going to do it again. I want you to watch and see how that balloon tilts forward. Now let's see what happens when he does it with the vacuum cleaner. Does the balloon tilt forward or does it stay pretty much upright? Doesn't fall forward until the very end. Now it's very subtle, and you may need to run that back and look at it again. But the car itself, as the balloon almost is collapsed, actually backs up a little bit. And you notice how quickly he turns off the vacuum cleaner. The other thing is you'll notice how long that straw is. Why is the straw that long? Wouldn't it work just as well if it was half that length? Or is he using it as a spacer for the vacuum cleaner? Let's have a look at a couple things here real quick. Well, here we have a helium balloon. Now notice it's more or less sitting in the same position. It's not really moving around a little bit. This is its stable position. If I want to move it, I have to apply a force to it. This is Newton's first law. A body at rest or a body in uniform motion will remain at rest or in uniform motion unless acted upon by an unbalanced force. This body is at rest. There's an unbalanced force. Now Pennywise, the dancing scientist, will conduct an experiment. Well, what did we see there? I simply put a vacuum hose next to the balloon, and when I turned it on, the balloon moved towards the vacuum hose. There was a force that moved that balloon backwards. What was that force? Well, if the vacuum caused an area of low pressure, the atmospheric pressure on the other side of the balloon would have tried to push it into that area of low pressure. But wait, there's more. Well now, isn't that fascinating? So not only was the balloon pulled towards the vacuum hose, it was also pulled towards the hairdryer. The vacuum drew air in, whereas the hairdryer pushed it out. What's in common with both of these? What you have here is air movement. It doesn't matter what direction it's in. So let's look at a basic physics principle and see what's happening here. The car doesn't move not because they're sucking all the exhaust out of the straw, or they're creating a vacuum behind it so there's nothing to push against. All they're doing is they're moving air, and they're using something called the Bernoulli principle. What's happening is the fact that there is air movement either with the vacuum hose or with the hairdryer. It's causing a low pressure, and just like the balloon, the car is literally being pushed backwards equal to the amount of the thrust of that straw. Notice it was a rather low thrust, and it's a very light car. Again, notice the spacing of the straw. He experimented with this to get the effect that he wanted. Now this is called a Venturi tube. It's a standard physics experiment for introductory physics. Now right over my head you'll see a plastic hose. That is an air supply. And that goes into a tube that has several sections. It has a wide section, it has a narrow section, and it has another wide section. And as you can see, there is a tube attached to each of those sections, and there's some colored fluid in it. Notice that all the levels of the fluid are equal. Now when he puts air under pressure into that first part of the tube, what will happen is the air will expand a little bit to fill the available space, and then it'll get crushed down a little bit to go into that smaller tube. Now, as it goes from the large tube to the small tube, there's going to be a little bit of resistance. And as a result, when the air goes in, I think it's pretty intuitive that the air pressure in that tube will go up slightly, and that will cause the fluid in that particular column to go down. There's no restriction as it goes from the small tube to the large tube. So the fluid level in that third tube, the one on the far left, should remain about the same. But what's going to happen in the narrow section of the tube? Remember, what goes in one side has to go out the other side. And if you suddenly choke down that tube, what you have to do is you have to put the air through it at a much higher velocity in order to get the same volume of air over a period of time through that section of the tube. Will the fluid in the middle tube go up because the air pressure decreased, or will it go down because it increased? Let's see what happens. Now, when you see the fluid in the tube start to move, that's when he's turned on the air. Well, there you go. Now, because the air is coming in from the right, the highest pressure is going to be in that first section, the wide section of the tube, and then it's going to get choked down to go into the narrow section, And that'll cause a little resistance, and that'll cause that part of the tube to be a little higher in pressure. And then as it goes into the smaller diameter tube, it has to speed up significantly in order to get the same volume of air through per unit time, volumetric. And as you see, the pressure dropped, and as a result, the fluid was pushed higher up into the tube towards the lower pressure. You get to the third section of the tube on the left, no real change. The water's pretty much where it started. And that, ladies and gentlemen, is how airplanes work. Now, you'll notice that you have two streams of air coming into the front of the wing from the left. The blue stream goes up over the top of the wing, and the red stream goes below it. The blue stream has a longer path to travel than the red stream does, but it has to meet the red stream at the exact same spot at the other end of the wing. As a result, that air that moves over the top of the wing has to move faster because it has farther to go in order to meet up with the corresponding air coming underneath the wing, which has a shorter path. As a result of that, you have higher velocity air on top of the wing, and due to the Bernoulli effect, what happens as you increase the velocity of the air, you decrease the pressure. As a result, the higher pressure is below the wing, and there's lower pressure above it, and the wing is pushed up. This is an excellent example of pressure differential without a container. I don't see a container on that diagram anywhere. Do you, Nathan? Now that we know what's going on, let's have a look at this rocket and see whether or not it's actually going into space. Now, space is defined as an area of very low pressure, a vacuum. Now, as the rocket goes up in the atmosphere, the pressure of the air around it will decrease. Well, what's happening to the pressure of that rocket plume? You're getting high velocity gas being thrown out the back of that rocket. Now, here at sea level, is the pressure in that plume with that high velocity gas going to be higher than the pressure of the atmosphere around it? No, it won't. And as a result, the rocket plume is compressed into a long, thin, straight flame. Let's see what happens as it gets higher in the atmosphere and atmospheric pressure drops. Okay, so here is the launch. Now, notice the width of the flame as it goes up. This is very important, and this is how you can tell rockets actually go into space rather than curving back. Let's look at the next shot. Same rocket, almost looks like a hoop skirt now. Okay, keep going. Get the exposure down there, guy. Look how wide that is. It's almost cascading out the back because there's no air pressure to press it in. Now it's just widening right out. That's going into space. So you see, once again, you're having somebody that is taking advantage of a well-known physics principle, whether they understand that principle and are doing this to deceive people, or they're just ignorant of it and thought maybe they were sucking the air out of the exhaust or something or other. You know, it's not good scientific reasoning. And anybody that has had some basic training in physics at the upper high school or even freshman college level would be able to tell them about this principle. A gas pump works on this principle to measure the volume of gasoline you're pumping into your tank. I mean, it's an everyday occurrence that we all see. This is how a pitot tube on an aircraft works to determine the airspeed of the aircraft. That's the little tube that sticks out the wing or is on the side of the fuselage. So, once again, this is Bob the Science Guy signing out from Northern Michigan. Thank you again for this opportunity to correct the physics knowledge deficits of the science denial community. Take care, everyone.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. the science guy.